Hello all. In today's lecture, we will be demonstrating the use of Unet architecture in order for image segmentation. So, here is the program code. Initially importing the necessary libraries. So, firstly we import the warnings in order to avoid the warnings being displayed after every execution or after every epoch. We make use of importing warnings and filtering out or ignoring these warnings. Then coming to importing the necessary libraries as in TensorFlow and Keras, as well as NumPy and Matplotlib. So, TensorFlow is imported as TF. This is required because Unet is a deep neural network architecture. So, that comes along with the TensorFlow library. From TensorFlow Keras pre-processing submodule, we import the image data generator. So, this image data generator is required for data augmentation or image augmentation as well as in the process of segmentation. So, segmentation is nothing but extracting the most important features in the image. So, for that purpose we will have to have an original image. Along with the original image there needs to be a necessity of a mask. So, mask is nothing but a binary image. Sometimes it could be a multi-class image as well, but if it is a binary image, the features which are important or to be extracted, those could be indicated with the help of ones, which are unimportant or which lies in the background, those could be indicated with the help of 0. So, image data generator is required in order to generate the image as well as the corresponding mask. Then from TensorFlow Keras models submodule, we import the model. So, we try to build the Unet architecture. So, Unet architecture is a symmetric architecture which works something like a encoder and decoder. So, in the encoding end we try to downsample, that is we try to extract more and more number of features. So, we start with less number of filters so that more information has been extracted. Then as we pass on in the encoding architecture, we try to strengthen the filtering process, so that even the very depth information can be extracted. So, same thing happens or opposite way it happens in the decoding part. There we have less number of filters and then go to the more number of filters, that is we try to maximize the resolution in case of a decoding. So, filters will be used more at the decoding starting part and less number of filters at the end. So, in order to build the Unet architecture we need this model. Then from TensorFlow Keras layers we import the input layer, so to have the input components. Then we have the convolution layer to perform the convolution, and then comes the max pooling. So, to downsample, as mentioned earlier, we need to downsample the images so that we try to get the maximum information or try to extract the features. So, for that we need this max pooling. And then we perform convolution 2D transpose. So, this performs like a convolutional 2D acts as the encoder, whereas the transpose acts as the decoder. And then we concatenate, we try to add some skip connections, that is why we need this concatenation. And to deal with numbers or arrays we need this NumPy, and for plotting we need this Matplotlib library. Now coming to defining or writing a function for dice coefficient and the Jaccard index. So, these are the two metrics which are being used in this program or used in this Unet architecture in order to understand how good is the predicted output with respect to the ground truth. So, ground truth is always present. Now, what is the amount of overlapping between the ground truth and the predicted output? That is determined in terms of dice coefficient and the Jaccard index. So, let us mathematically represent this dice coefficient and the Jaccard index. So, dice coefficient can be represented as 2 times intersection of A and B divided by A plus B. So, A refers to the number of foreground pixels in the ground image. So, A refers to the foreground pixels in the ground truth, or we can say ground image, and B refers to foreground pixels in the predicted image. In the predicted image. So, when we take this ratio lies in the range of 0 to 1. So, the more the number, the better the performance of the model. So, this is about the dice coefficient. Now, coming to the Jaccard index. Also called as intersection over union. So, we perform the intersection of the ground truth and the predicted image, and then take the union of them, and then take the union of them. So, this is the intersected part, what is common in both. So, the overlapping part divided by the total of the foreground pixels in the ground truth as well as the predicted image. So, even here the Jaccard index lies in the range 0, 1. So, 0 means there is very minimal overlapping, or there is minimal extraction or the segmentation which has been done, whereas 1 refers to the highest performance of the Unet architecture. So, these two are mathematically represented and the code is written for the same. So, we are defining the dice coefficient based on what is the ground truth and based on what has been predicted. And the smooth equal to e power minus 6, this is just required in order to avoid the division by 0, because in both the cases we have seen that it is a fraction, we have some component in the numerator and the denominator. In order to avoid division by 0, we add a small value e power minus 6. So, what is our ground truth? It is the actual true value what was available in the given set of folders or directories which are present. And then what is prediction? The predicted output by the Unet architecture. So, intersection could be given as y true f into y prediction f, and then we are getting the dice coefficient 2 times intersection divided by addition of A and B, where A refers to the foreground pixels. So, when we say foreground pixels, it refers to the region of interest, whereas background pixels refers to the unimportant portions in the image. So, which could be represented as 1 and 0. So, region of interest as 1 and the background as 0. So, same way defining the Jaccard index based on the true or the ground truth as well as the predicted output, and also here we make use of e power minus 6 as the one constant value in order to avoid the division by 0. So, once again getting the true value and the predicted value, we need the intersection as well as the union. So, in order to perform intersection we multiply them, and to get the union what we do is A plus B minus the intersection. So, both mean the same. When we have to get the union of two sets, then we can add them and perform subtract the intersection part. So, this will give us the Jaccard index. So, once we define the performance metrics, now let us see what data set we have used and from where it has been derived. So, we import another two libraries called as OS and Glob. So, OS is required in order to handle the operating system level files or functions, and then importing the Glob. This is required in order to get the pattern level folder handling or directory handling. So, the data set what has been used here in order to demonstrate Unet is the MedPlant data set. So, this MedPlant data set is a real data set which is obtained for us for this NPTEL course through a collaboration. So, Professor Bindu has given this, she has created this data set and was readily agreeing to give us the data set. So, this is a real data set which has been created. So, this medicinal plant data set has 5 different species of medicinal plants. A medicinal plant something like aloe vera, basil leaves or tulsi leaves. So, what we are trying to do is we have images of all these medicinal plants, like 5 species of medicinal plants, and we try to get only the leaf portion from the entire image, extract only the leaf portion so that we can further process it. So, now creating the training directory and the test directory. So, we have to sort the 5 species in the alphabetical order and join each of the each of the species. I already mentioned there are 5 species. So, you have to join all the 5 species one over the one after the other in the alphabetical order. So, that we can have a separate folder for training set and a separate directory or a folder for the test set. After once we get these folders ready, we let us print the length of the training directory, the length of the test directory and how many species are present. Also we need the image generators, especially for the image generation as well as the mask generation. So, already mentioned we need the images and we need a mask which is nothing like a original image, but mostly it will be binary, and this will help us in comparing the original image with the mask. And then if the overlapping is there, if the features are same as that of the mask and the original image, the value would be 1, otherwise the value would be 0. So, image generator or image data generator, we have to rescale those images what are present in these directories. We will rescale so that we get in the range 0 and 1. So, we mostly consider this as a grayscale image. So, which can have values 256 different intensity values varying from 0 to 255. So, suppose we want it to be varying in the range 0 to 1. When we normalize, then what we do is we divide it by the maximum value. Suppose we have intensity value as 0 in the image, then it is 0 by 255. Suppose we have intensity value as 1 in the image, then it is 1 by 255. Suppose the intensity value is say 50, then 50 by 255. So, this will make us get the values in the range 0 and 1. So, nothing but we are performing the normalization. So, printing of all the species and the plant species which are present as well as their length. So, we have found 5 plant species in the training data. So, we had already given the print statement above. Also found 5 plant species in the test data, and the plant species are Annona muricata, Cestrum diurnum, Nicanthes arbortritis, Ocimum tenuifolium and Psidium guajava. So, these are the medicinal plants or the scientific names for the medicinal plants. Now, creating a generator that will pair both the image and the mask batches. So, when we say mask, we need to have some batch size also. So, let us assume some batch size, so that in the training phase, after every batch or after every batch size of 4, the model weights will be updated, so that the gradients are updated. So, now defining this create segmentation generator, this is the function which we are creating on the image directory as well as the mask directory. So, we are taking into consideration both the original image as well as the mask which we have created in batch size of 4. Then we have to sort all the images in the alphabetical order, both the mask as well as the images. So, this entire code cell is about arranging the plant species in the alphabetical order and checking whether there are a sufficient number of masks available for the number of images. So, the basic the fundamental concept here is for every image there should be a mask. So, if we have say 256 images, then there should be 256 masks, or if there are 200 images, there should be 200 masks. So, this code cell is about finding the respective mask for the image, corresponding mask for the image. So, now if not image files, if we are not able to find the image files, then no image is found. So, print that particular error, then verifying the corresponding mask exist or no. So, this exercise is all about finding the mask file for the corresponding image. So, mask file, I am creating an empty list. For every image file in the image files, you have to take the base name, you have to take the mask file name and then attach or stitch each other. So, if from the operating system there is a path existing to the mask file, then append the mask file. Otherwise, mention that there is no mask available for a particular image, but we have made sure that there is a mask for every image present in the training set. And once that particular condition is been checked, then we are printing the length of the image files as well as the length of the mask file, so that we do not miss any of the mask. Now, if the length of the mask file is equal to 0, then there is no match available, or there is no matching mask for the image. So, that is the value error to be erased. That is one condition. If not, directly go to the generator function. So, what is this generator function doing? So, we are creating a generator function and starting with the index 0. So, we are starting with the first plant species. We have a separate directory for every species. So, suppose I am taking the first species, then we start with index number 0 while it is true, while the index is 0. Take a separate list for image, take a separate list for mask, and then for every integer in the range batch size, that is 4, we have to check whether the index is greater than the length of the image files. If it is greater, then index will be equal to 0, because it should not exceed the length of the number of images. So, it is very simple here. If it is exceeding, then you have to start back the loop. Then load the image. With respect to the index. So, index goes on increasing every iteration, every looping, it goes on increasing. So, we have started with index 0. Once we reach every index, say suppose index equal to 0, then the target size or the image size will be 128 cross 128. So, 128 pixels we consider as height, 128 pixels, another 128 pixels as in the x direction. So, and as mentioned earlier, we consider it as a grayscale image for easier processing. So, once we find the image, normalize those images. So, image to array conversion we are doing, and those image array we will have to normalize, so that we have all the values like binary values 0 and 1. So, 1 means it is the foreground, 0 means it is the background image, which is not necessary, background is not important. Now, what if the index value is less than the length of the mask file? Then what we have to do is again process this particular loop. So, take a target size image of 128 cross 128. Once again, this is height, and this is the number of pixels in the x direction, y direction and the x direction. Once again, it is a grayscale image what we are considering, and then we have to pre-process even the mask and normalize, so that we get the value from 0 to 1 only, 0 and 1, nothing but a binary image. Once we have all the mask for all the corresponding images, append those masks one over the other, and the index has to loop every iteration, it has to increment by a value of 1, and then we have an array for batch images as well as batch mask. So, put together we have generated, or we have created a function so that it has generated the image and the mask. Basically, it is generating a mask for every image, and the batch size considered is 4 here. So, creating generators for training and test data. So, once now the image and the mask is generated, we have to separate it as training and the testing. So, create the segmentation generator on the training image directory as well as training mask directory in length of batch size, that is 4. That means, we are considering 4 images at a time and then updating the weights. Same way, create the segmentation generator on the test image directory as well as the test mask directory in batch size of 4. So, totally we come across 216 images and the corresponding mask in the training phase, and 52 images and the corresponding mask in the testing phase. Now, coming to the actual model building, that is the Unet architecture. As mentioned earlier, it has two portions, the encoding part and the decoding part. In the encoding part, we downsample, whereas in the decoding part, we upsample. So, we can see the downsampling and the upsampling. We are building a Unet architecture. Input shape size, we have already mentioned as 128 cross 128. So, height and width, and this 1 refers to the number of channels. So, whenever the channel is equal to 1, it refers to a grayscale image. Whenever it is 3, it is a RGB image. Since we are considering grayscale, it happens to be 1. So, the inputs what we are considering, or input images, they are in the shape as defined earlier, 128 cross 128 cross 1. So, now let us see what are the components coming under this Unet architecture. We have the convolution process, we have the number of filters, then we have the kernel size, activation function, padding if required, and what are the inputs that are going to this layer. Similarly, we have another feature map, output feature map C1, which is again the convolution of 64 different filters. Then we have the kernel size as 3 cross 3, then we have the activation function as ReLU, padding will be same, and the input to this would be the previous C1 or the feature map. And then we have the max pooling, which performs the downsampling. So, what exactly is done here is 64 refers to the number of filters. So, we have 64 different outputs from this convolutional layer after performing the convolution over the input image of size 128 cross 128 cross 1, and then we have a kernel size of 3. So, if we have an image, consider this image of size 4 cross 4. What this 3 cross 3 kernel does is, it takes a sliding window, this 3 cross 3 kernel sizes, it takes a 3 cross 3 sliding window and attends only these 9 pixels at a time. In the next iteration, what happens is, it takes another 3 cross 3. So, same way the sliding happens and it considers only 3 cross 3 pixels at a time. So, this is required in order to go through the image in detail. Otherwise, when we take the entire image and the kernel of the same size, what happens is there might be some minute features which would be missed, or minute information which might be lost. So, here every pixel is being attended and it has been compared with the filter, and there is a ReLU activation function. So, what this ReLU does is, it takes the maximum of 0 or the input pixel value. So, if the pixel is important, if the feature is present, then it is going with this intensity value, that is x is nothing but the input. So, whatever intensity value we have, so 56. So, 0 comma 56. So, this 56 is important in order to extract the feature, or that particular feature is important. So, either 0 or the maximum value. So, that is why we make use of the ReLU function here, activation function. Now, padding is same, padding is required in order to make the input vector size of the same size, because the input vector could be varying. When we go layer by layer, the vector size could be different, or the image size could be different. So, by making use of padding, either pre-padding or post-padding, we could add zeros and make it of uniform length. And then we have this max pooling. Max pooling, 2 dimensional, we make use of 2 here. So, what happens is, 2 cross 2 values are taken at a time. Suppose say pixel value is 0, then we have something like 20, this is 12 and this is 2. Then the maximum value of this is 20. So, the output of this 2 cross 2 window is 20. So, what happens is, this 2 cross 2 window is converted into 1 pixel value or 1 intensity value. So, what is happening is, we are trying to get the features which are important or which are having the maximum value. That is why we are making use of max pooling. There are many pooling processes like min pooling, average pooling, they have its own significance, but in case of segmentation, what features are important matters a lot. So, whichever pixel is having the highest intensity value, that needs to be figured out or that needs to be extracted, that is why we take this max pooling. So, layer by layer when we pass on, we are increasing the number of filters here. So, this is low level filtering, this is better filtering, and then as we process, the filtering becomes little tedious. So, with the low level feature extraction to high level feature extraction. So, from 64 filters, we are now increasing to 128, then 256, 512 and 1024. This is about the encoding part. So, we can see that in the encoding part, we have the convolution, we make use of one activation function, padding and the necessary inputs. The previous layer inputs will act as the previous layer output will act as the input to the next layer. So, this is the architecture of the encoder from C1 to C5. Now same thing should happen in the decoding side, but in a reverse manner. That is why we make use of the transpose function. So we try to reduce the number of filters. So starting with 512, then it reduces to 256, 128, 64, and then finally one output that we require. So convolution 2D transpose, we start with the 512 filters, and then we have 2 cross 2 kernel size, which is going in a stride of 2 cross 2. Once again equal input vector length, that is why we are padding it, and this is the input from the previous feature map. So likewise we have same kind of decoding architecture. And then at the dense layer or at the output layer, once again we have the convolution. So there is only one filter, and then there is only one kernel size, one cross kernel size of 1. Activation function is sigmoid, and the input which comes to this output layer is C9, that is from the feature map, the output of the previous feature map. So what is the importance of the sigmoid function is, it is used in case of a binary classification. So the sigmoid function, it is a S-shaped function. Sigmoid function is a S-shaped function which can vary from 0 to 1. So we can take the values from values varying from 0 to 1. So the sigmoid function could be defined in this way: sigma of x is 1 divided by 1 plus e power minus x. So x is the input value that needs to be fit. So in case of a data set, a normal tabular data set, the x value could vary from minus infinity to infinity. So suppose I take it the same way, then 1 plus e power minus of minus infinity 1 divided by e power infinity. So anything power infinity is infinity, we get 1 plus infinity as infinity. So the value is 0 here. So the value starts from 0. Now same way, if I take the maximum value e power minus of infinity, so this is 1 by infinity. So 1 by infinity is 0. So this ratio will be equal to 1. So we have started from the minimum value as minus infinity, we have reached up to the maximum value of infinity, and we see that the sigmoid function gives the value in the range 0 to 1. So now when we think of a pixel value, the pixel value could be 0, it could be the maximum value could be 255. So when we try to update that value in place of x, either 0 to 255, our value still lies from 0 to 1 itself. So minimum value to the maximum value. So that is the importance of a sigmoid function, because whenever we deal with the sigmoid function, we can have the values between 0 to 1. So whenever the value is greater than 0.5, we can keep a threshold. We can have a threshold of, say, if the probability of this or sigmoid value is greater than or equal to 0.5, then it is class 1. If it is less than 0.5, then this would be class 0. So the same concept helps us. If it is class 1, then it is a foreground pixel, nothing but the region of interest. If it is class 0 or probability is less than 0.5, then it comes in the background and it is the unimportant feature. So whenever we deal with the binary numbers or binary classification, we need this sigmoid function. So finally we build this Unet model with the help of set of inputs and outputs, and then return the model. Okay. Then once we have built this Unet architecture, we are compiling or training this model. So optimizer, we are making use of Adam optimizer, and let the learning rate be e power minus 4. And the loss function, what we are using is binary cross entropy, because it holds good for a binary classification. And the metrics, as mentioned earlier, we are making use of the dice coefficient and the Jacquard index. So, let us now see the model summary, the model which is built. So, this is the model summary. So, what we need to observe here is mainly the output shape. Okay. So, 128 cross 128 cross 1. So, this is the height, this is the width, and this is the number of channel. So, as we progress, we have seen the number of filters being increased, and accordingly the output shape, we can see the number of channels also increases. So, how do we get these parameters? It is based on this formula, mathematical representation. So, the number of parameters that comes with the convolutional layer is kernel height into kernel width into the number of input channels plus the bias associated with the channel and the output channel or the output layer. So, how do we calculate it for the first one? So, let us see how do we calculate it for this. So, kernel width and kernel height are 3 cross 3 into the input channel is 1 plus the bias 1 plus the output. So, that gives us 640. So, we see that kernel height was 3, kernel width is this, number of input channel is 1, bias involved is 1, and 64 is the number of filters being used. So, that is why 3 into 3 9, this is 9 plus 1 into 64, which will be 10 into 64, which is 640. So, the number of parameters are 640 in number. Same thing when we try to do for the next layer, that is this layer, then kernel width and height we have not changed. If you remember, it was 3 cross 3 into now the number of input channels from the previous one, from the previous output feature map, it is going to the next one. So, this happens to be 64 plus 1 into 64. So, this would be giving us 36,928 parameters. Likewise, we should be able to calculate for every layer that we have built. So, that is about the number of parameters that are required or trainable parameters required in the convolutional layer or a 2D convolution. Now, let us have the history for the model that has been built based on the number of steps or the number of epochs that we need. So, number of steps in the training set, let it be 200. Once again, it depends on the data set size. Since the data set size is huge, we can use about 200 steps in the training phase. Similarly, in the test phase, we can make use of 50 different steps. So, model is fit on the training generated, then the number of steps per epoch will be same as the one which we have defined here, and on the validation data or on the test data, the number of steps being assigned is 50. So, based on this, we have the epochs and their corresponding dice coefficient and Jacquard, both for the training as well as the validation or training as well as the test. So, we can see that as the epochs progress, the dice coefficient are also increasing. So, it started from somewhere like 0.38 and it is going up to 0.97. So, this is a very good segmentation which has taken place. Even the Jacquard index, which we see as 0.23 going up to 0.95 with the number of epochs being 20. So, same thing holds good even in case of loss as well as validation dice coefficient and validation Jacquard values. So, it is increasing. Now, coming to the prediction part, how exactly the segmentation takes place. So, as mentioned earlier, whenever the threshold value is greater than 0.5, we consider it as an important feature. Whenever it is less than 0.5, we take it as a background. So, the same concept is being used here. So, we make use of the images, we make use of the mask and go to the next prediction part, whatever image that needs to be predicted. So, model predict on all the test images. Whenever the prediction value is greater than 0.5, then take it as the important feature, put it to the bin or predict that particular part. Also print the corresponding dice coefficient and the Jaccard values for the test mask as well as what is being predicted. And whatever prediction has been done, the dice coefficient or the Jaccard, it is in the form of a NumPy array, a single value. So, that value could be seen here. Dice coefficient is 0.97 and Jaccard value is 0.95, which are very apt in case of image segmentation. Now, coming to the final part, so let us see in terms of plotting how exactly a test image looks like, what is meant by a mask and what is a predicted mask. So, there is a test image which is given for testing. We can see that there are 3 different leaves, but out of which the 2 leaves they have gone out of the image, or some portion of the image is not being displayed properly. But we see the middle one, we have all the corners or edges being reflected properly. So, this is the test image on which this is the true mask. The shape of the image or the original shape of this particular leaf is already been displayed here or described. Now, what has been predicted? If we try to compare this predicted one with the true mask, we can see some differences. That is why the Jaccard or the dice coefficient is not exactly equal to 1, because there is difference in terms of corners. So, if we see this corner and this particular corner, it is not perfectly aligned. Or if we see this corner, this is taking a shape of a triangle, but here it is like a rectangle or a square shape. So, let us see how exactly we have done this plotting, taking once again making use of the figure function, 12 inches in width and 4 inches in height. We make use of the subplot function. So, we take one row, 3 columns, and in the first column, second column and the third column, what exactly we need to display. That is the test image, and in the second column we need to have the true mask, and in the third column we want to have the predicted mask. So, subplot function will help us in dividing the figure into different rows and columns, rows, columns and the position. So, we want to give some title as well as show the image, the first image or the 0th index image. So, here squeezing of the image or squeezing while showing the image means we take away the channel. We make use of only 128 cross 128 pixel, that is the height and the width only. We try to avoid that 1, the channel 1, and the color map is of course the grey. So, same thing is been shown here. So, this is for the 0th index in the test data set. Now, what if we want to plot more number of images? Then we can make use of this particular code cell. So, number of samples, say suppose I want to have 4 images or 5 images. So, minimum and the maximum values I want to define, okay, starting from the 0th index. So, accordingly I will have to give a figure size also, so that the number of samples and the figure size also should match each other, otherwise there will be overlapping between the images. So, for every integer in the range, the number of samples being defined. Subplot also varies with respect to the number of samples, because in the subplot the first one refers to the rows, the second value refers to the column, and the third one refers to the position where exactly we want the image to be plotted. So, we want the test image, the true mask and the predicted mask for 4 different samples. So, the same thing can be seen. So, we see that there is difference between the true mask and the predicted mask, at least in few corners or edges. So, in this lecture we have seen the demonstration of Unet architecture for image segmentation. So, initially we started with the image data generator, wherein we tried to get a mask for every image, and we performed some kind of pre-processing like rescaling of the data, shrinking of the data or normalizing the data. So, all these pre-processing came as a part of image data generator. Then we built the model, Unet architecture model, and then defined 2 matrices like the dice coefficient and the Jaccard index. So, with the help of these 2 metrics, we have defined how the performance varies with respect to the true or the ground truth and the predicted mask. Thank you.